The water in our oceans consists of a mixture of normal water H2O and a small proportion of heavy water D2O. The hydrogen isotope deuterium-D can be extracted from heavy water using various processes. Deuterium is the fuel needed to operate a fusion power plant. If this fuel could be used, 1 liter of ocean water would have the same amount of energy as several hundred liters of crude oil. For this reason, intensive research has been carried out for several decades into how controlled nuclear fusion could be achieved in order to utilize this inexhaustible source of energy. The conditions required to ignite a fusion are known and are described by the so-called Lawson criterion. According to this criterion, the product of temperature, pressure and reaction time must exceed a certain minimum value. Even the simplest deuterium-tritium fusion requires ignition temperatures of over 100 million K at a pressure of a few bar. However, the Lawson criterion is not a law of nature. It merely states that the smaller the distance between two atomic nuclei as a result of the pressure and the greater their kinetic energy as a result of the temperature, the more likely they are to fuse. If the temperature and pressure are sufficiently high, more collisions can take place over a longer period of time. If the temperature and pressure are not sufficiently high, even the longer period of time is of no use. Successful nuclear fusion is therefore mainly dependent on the product of pressure and temperature. As there are no materials that can withstand such temperatures, reactor concepts such as tokamaks and stellarators have been developed that use electromagnetic fields to keep the fuel away from reactor walls and heat it up at the same time. The deuterium-tritium gas mixture becomes conductive plasma when heated and can thus be trapped in magnetic fields. However, the commissioning of operational fusion power plants is not expected for decades, if ever. In the following, a completely new hydraulic process, HINF, is presented, which offers several advantages compared to known concepts. Deuterium-tritium fusion takes place in liquid and does not damage any components. The deuterium-tritium gas can be heated to extreme temperatures. Extreme pressures prevail at the same time. The energy required for the start is distributed intermitting over a longer period of time. A fusion process is repeated up to 1,000 times per second, depending on the size of the reactor. The fusion reactor can be produced cost-effectively with current technology. In the reactor, hydraulic pressure waves interact with thermodynamic changes of state, which are not generally known and are therefore explained here in advance. A point-shaped sound source in three-dimensional space, such as an exploding grenade, generates a so-called spherical wave. The sound pressure of this explosion changes in the ratio 1 divided by distance, i.e., at twice the distance the sound pressure is halved. Assuming the grenade explodes in the center of a large hollow sphere, its pressure wave, which is weakened with distance, reaches the inner wall of the hollow sphere at the speed of sound and is reflected there as if by a concave mirror. This reflected spherical wave then travels back to the center of the hollow sphere and is amplified in the ratio of 1 divided by distance. The behavior of a fictitious pressure wave moving in a liquid-filled hollow sphere is illustrated in an animation. The wave starts simultaneously at the entire wall of the sphere, meets in the center and runs back to the wall. The front part of this fictitious wave has a weak pressure reduction, the rear part a strong pressure increase. The wave amplitudes increase on the way to the center of the sphere and decrease on the way back. While any pressure increase of the wave at the point-shaped center of the sphere is infinitely large, the pressure reduction there is only limited by the boiling pressure of the liquid. Pressure waves can propagate in elastic media such as gases, liquids, and solids. They are generated by moving air, for example with a loudspeaker membrane. Without mass transport, this wave propagates in the medium at the speed of sound, whereby the speed of sound is mainly dependent on the elasticity and density of the medium. The speed of sound in water is around 1,500 meters per second. The generation of pressure waves is explained using the example of a piston connected to a long pipe in another animation. The system is closed and filled with liquid. Moving the piston triggers a pressure wave. The pressure amplitude P of this pressure wave is calculated using the simple formula. P equals A times rho times V, where A is the speed of sound and rho is the density of the liquid. The speed of the piston is versus. A calculation example illustrates the magnitude of the piston movement and the deformation of the inner wall. A pressure wave of length L equal to 1 meter with a pressure amplitude P of 1 bar, i.e., 0.1 megapascals, is to be generated with the piston. The required piston speed V is therefore 0.067 meters per second, according to the above equation. The pressure wave propagates at the speed of sound and covers a distance of 1,500 meters per second. A pressure wave 1 meter long then takes 0.67 milliseconds to travel. In the same time, the piston moves inwards by 45 micrometers. The required piston force corresponds to the shaft pressure and in this example is 10 newtons per square centimeter of piston surface. The reactor therefore requires actuators analogous to the piston, which increase or decrease its diameter uniformly in the micrometer range. The resulting movement of the reactor wall generates the desired spherical pressure wave in the reactor fluid. The use of piezo actuators to generate pressure waves is ideal because high actuating forces and high actuating speeds can be generated. The stroke can also be precisely controlled. Piezo actuators are made of special crystalline or ceramic material that changes its structure and thus, for example, its length under the influence of electric fields. This deformation is very small. Commercially available actuators with a length of 100 mm and a cross-section of 100 mm achieve maximum strokes of a few hundred micrometers and actuating forces in the kilonewton range. A maximum stroke frequency of 30 kHz is possible. The stroke of these actuators is directly proportional to the applied electrical control voltage. The piezo effect is reversible. If the actuator is deformed by external forces, electrical energy is generated. If an actuator is controlled with a sawtooth-shaped voltage, its stroke speed is also constant. As a result, pressure waves with a constant amplitude are generated with this type of control. If the reactor wall moves outwards, the pressure is reduced. If it moves inwards, the pressure is increased. The wavelength depends directly on the duration of the movement. It is equal to the distance the wave travels during the piston movement. In this way, complex-shaped pressure waves can be generated. They propagate at a constant speed of sound, while the pressure amplitudes depend directly on the wall velocity. Another remarkable property of pressure waves is their behavior when superimposed. If, for example, two waves coming from different directions meet, the sum of their amplitudes would be measured at the meeting point, after which these waves separate and appear in their original form. Pressure waves can therefore not influence each other. The following animation shows two different pressure waves that meet in opposite directions in a pipe. It follows that a complex-shaped spherical pressure wave generated at the reactor wall travels to the center of the reactor with increasing pressure amplitude and then arrives at the reactor wall again in its original form with decreasing pressure amplitude. If damping caused by fluid friction and a not completely constant speed of sound are neglected, the speed of sound of many liquids increases slightly with increasing pressure, which means that different areas of a pressure wave propagate at different speeds. This causes a certain deformation of the waves. With longer wave travel times, the areas of high pressure amplitudes shift into the wave head while the areas of low amplitudes fall back, resulting in a steeper wave front and a delayed wave end, as can be seen in the following illustration. This behavior of the duck wave deformation is advantageous for the desired application. Three further points are important for the later consideration of the fusion reactor. The solubility of gases in liquids. Gases can be dissolved in liquids, the amount of which depends on the liquid, the gas, the temperature of the liquid and the pressure. In general, the amount that can be dissolved increases with increasing pressure and decreasing temperature. The dissolution process takes place slowly by surface diffusion. With decreasing pressure, spontaneous outgassing begins. When a liquid with dissolved gas evaporates, the gas and vapor are completely separated. The solubility of gases varies. For example, relatively large quantities of carbonic acid can be dissolved in water, whereas hydrogen and its isotopes deuterium and tritium can only be dissolved in comparatively small quantities. Evaporation and condensation. If the boiling pressure of a liquid falls below the temperature-dependent boiling pressure, spontaneous vaporization occurs. A subsequent increase in pressure causes spontaneous condensation. These phenomena can be observed, for example, in cavitation processes in hydraulic systems. Geometry of the reactor. Only with perfect spherical geometry of the reactor wall do waves with any positive pressure amplitudes in the infinitely small reactor center reach the amplitude value infinity. In contrast, waves with any negative pressure drops can only reach a value that corresponds to the current boiling pressure of the reactor fluid. Description of the reactor. The reactor consists of a thin-walled hollow sphere that is completely filled with liquid. This liquid can be water, for example, which has been completely freed of all the gases it contains. A precisely defined quantity of the gases deuterium and tritium is then dissolved in the liquid. The outer wall of the reactor is thick-walled and concentric to the inner hollow sphere. Actuators are located between the inner and outer reactor walls at regular and tight intervals, which are supported on the outside and can slightly deform the inner hollow sphere. The space between the inner and outer reactor walls is filled with gas, the pressure of which can be changed. The gas pressure is approximately as high as the average internal pressure in the reactor. Without this gas pressure, the thin inner reactor shell would not be able to withstand the desired system pressure. An external control unit is responsible for all functional processes and the operation of the reactor. Other external components include a preheating system that is hydraulically connected to the inside of the reactor. It ensures that the reactor fluid is heated to a precisely defined temperature between 400 Kelvin and 600 Kelvin before starting. In addition, a system is required that keeps the average pressure of the reactor fluid constant at an exact value between 0.1 and 3 megapascals. If, for example, a desired system pressure of 2 megapascals is selected for the reactor liquid, its boiling temperature is 488 Kelvin. To prevent steam from forming, the reactor liquid must be colder than 488 Kelvin, for example 475 Kelvin. A brief reduction in pressure to 1.5 megapascal would then fall just below its boiling point and lead to the formation of vapor bubbles. During fusion in the reactor, the two hydrogen isotopes fuse to form helium, which would disrupt the further fusion process. An external purification unit therefore removes the resulting helium and adds the spent deuterium and tritium back to the reactor fluid so that their solution content remains constant. The energy released in the reactor liquid and on the reactor walls during fusion is dissipated via heat exchangers and can be used to generate electricity, for example. The reactor is started in two phases: heating and pressurization of the reactor fluid with external components using energy. Then periodic generation of special pressure waveforms by the actuators on the thin inner wall of the reactor. As these pressure waves deform slightly during operation, as already described, constant correction by the actuators is required. The frequency of these pressure waves must be precisely adapted to the size of the reactor. Their propagation speed is around 1,500 meters per second in water. This means that for a reactor with a diameter of 3 meters, the pressure wave travels through the reactor 500 times per second. In larger reactors, several pressure waves can be sent through the reactor at the same time. The length of the generated pressure wave must always be shorter than the reactor diameter, as otherwise the wave area with pressure reduction will be disturbed by overlapping. Generating the desired pressure wave with many actuators on the reactor wall requires a lot of electrical energy. It is therefore advantageous to generate the waveform step by step using periodic weak pulses, whereby damping of the pressure wave due to fluid friction must at least be compensated for. Functional sequences in the reactor. The complex pressure wave described above runs from the reactor wall to the center of the reactor, whereby its front pressure drop becomes greater and greater and then creates a spherical area in the center of the reactor liquid in which the system pressure falls below the boiling pressure. A cloud of many small gas bubbles then forms there. It is generally known that these gas bubbles have diameters ranging from 1 micrometer to 100 micrometers. The fate of a single vapor bubble is now to be investigated when its ambient pressure suddenly increases. The bubble initially contains vapor and the deuterium-tritium mixture previously dissolved in the vaporized water. The gas and vapor have the same temperature as the reactor liquid. The high pressure at the edge of the bubble accelerates the surrounding liquid, creating a new miniature spherical wave that compresses the bubble. The pressure on the inner bubble wall therefore rises above the boiling pressure, causing the vapor to condense there and the condensate to combine with the reactor liquid. The steam therefore offers no significant resistance to the pressure wave. The gas remaining in the bubble is compressed as the bubble diameter becomes smaller, whereby the pressure and temperature increase according to the laws of thermodynamic changes of state. The bubble reaches its smallest diameter when the inner gas pressure is exactly as high as the outer spherical wave pressure. At this point, under certain conditions, extremely high pressures and temperatures can develop inside the bubble, which can start a nuclear fusion. As the miniature spherical wave is no longer effective from this point onwards, it depends on where the event took place. In the center of the reactor, the pressures are extremely high for as long as the passage of the spherical wave on the reactor wall lasts. The larger the reactor, the longer this spherical wave can be. The aim of the reactor is to create optimum conditions to enable ignition of the compressed deuterium-tritium mixture. As already mentioned, the duration of the gas confinement also plays a role. This depends on the distance of the bubble from the reactor center. Extremely high pressure prevails in its immediate vicinity as long as the pressure wave generated in the reactor moves through the center. It will now be investigated which parameters improve the ignition conditions. The influence of pressure wave amplitude, reactor liquid temperature, and the amount of gas solution in the reactor liquid is calculated in 4 case studies. The product of maximum gas temperature and maximum compression pressure is used to estimate the probability of ignition. This is part of the Lawson criterion, which also includes the reaction time. Case A assumes that the vapor bubble contains only gas apart from condensate. Without condensate, the bubble would be completely filled with gas under normal conditions. The pressure wave leading to the implosion is assumed to be 1 megapascal near the bubble. The temperature of the reactor liquid is assumed to be 300 Kelvin. The radius of the bubble is 10 micrometers, whereby only the interesting range from 1 micrometer to 0 micrometer is shown in both diagrams. Since a pressure wave is completely reflected when it hits a solid wall or even a bubble wall, the amplitudes of the incoming and returning waves add up. A fictitious wave with an initial pressure of 2 megapascals is therefore used for the calculation. Initially, the spherical wave is greater than the compression pressure. However, the latter increases progressively, and at 120 megapascals there is pressure equilibrium with the wave pressure. The gas temperature in the lower diagram is then 10,000 Kelvin. A PT product of 1.4 times 10 to the 6 is calculated from the pressure and temperature. Case B differs from case A in that the temperature of the reactor liquid is assumed to be 500 Kelvin. The gas in the bubble then also has 500 Kelvin at the start of compression. This does not change the pressure equilibrium, but the final compression temperature rises to 20,000 Kelvin. A high temperature of the reactor liquid is therefore advantageous. However, with water as the reactor liquid, its temperature cannot be increased significantly above 500 Kelvin. There are then no separate steam and water phases. The changed parameter in case B increases the PT product to a value of 2.4 times 10 to the 6. Case C uses the parameters of case B, but assumes that a pressure wave of 100 megapascals approaches the area of the bubble cloud. When a bubble disintegrates, a pressure of 60,000 megapascals and a temperature of 120,000 Kelvin are generated. The PT product grows to 7.2 times 10 to the 9. As the pressures in the center of the bubble cloud are considerably higher, the PT product also increases. However, only in the inner area of this cloud. Case D differs from case C in that the amount of dissolved gas in the reactor liquid is lower. There is only 0.0001% gas in the bubbles compared to the full gas content under normal conditions. The pressure equilibrium is at 12 million megapascal, the maximum gas temperature at 1,300,000 Kelvin. The PT product is now 1.5 times 10 to the 12. Finally, the number of bubbles within a spherical cloud with a radius of 100 millimeters is to be estimated. An average bubble radius of 10 micrometers is assumed, and the volume of all bubbles should be only 1% of the cloud volume. It follows that there are about 10 billion bubbles in this cloud. In summary, it can be seen that almost any ignition conditions can be realized by a favorable choice of parameters, in particular by a low gas concentration. As already mentioned, the probability of nuclear fusion increases with the largest possible PT product. The tokamak reactor type plays an important role in current fusion research. In this concept, deuterium-tritium plasma is heated by strong magnetic fields in a torus-shaped reactor under vacuum conditions and kept at a distance from the reactor walls. At the same time, the plasma is moderately compressed by magnetic fields. The aim is to overcome the repulsive nuclear forces of the deuterium-tritium atoms through temperature-related high kinetic energy and some pressure so that the fusion product helium is formed. It is assumed that the plasma must be at least 100 million degrees hot. The plasma pressure, which is not known here, is probably in the lower MPa range. Assuming that this pressure is 100 bars equals 10 megapascals, this results in APT product of 1E9 for the tokamak reactor. This value is already clearly exceeded with case 3. Case D is 1,000 times higher. All the calculations shown above, which relate to the hydraulic fusion reactor, were carried out without taking into account fluid friction, radiation losses, losses due to heat conduction on bubble walls, etc., and assuming a perfect reactor geometry. The achievable maximum values of pressure and temperature are therefore lower. Nevertheless, the results show the great potential of this hydraulic concept, with which not only high temperatures but also high pressures can be realized at the same time, which significantly improves the ignition conditions of nuclear fusion.